Hi everyone, my name's Henry. I'm a postdoc at ANU and I work with Lisa Cooley predominantly. And today I'm going to be talking about some recent work I've been doing with the SAMI Galaxy Survey. Two things to note, this is entirely unrelated to what I did for my PhD. For my PhD, I did jet ISM interaction stuff, completely unrelated. Second thing to note is that the title of my talk is completely different from what's in the program, so apologies, but hopefully you'll find it interesting either way. So emission lines give us a window into the life and times of galaxies. So by using the ratios of different pairs of emission lines, we can classify them as being dominated by star formation, say, or being dominated by emission from a luminous AGN. Integral field spectroscopy is a particular kind of spectroscopy that gives us data cubes. So these give us an image at each wavelength and a spectrum at each pixel or spaxel. And these allow us to really closely examine the relationship between the underlying physical processes and the emergent emission lines. And so using integral field spectroscopy, for example, for these three galaxies, you can map out the fluxes of all the different emission lines across the face of a galaxy. And so in this way, you can spatially resolve regions dominated by star formation, regions dominated by evolved stars, so on and so forth. And by using the Doppler shift of the emission lines, you can also trace the gas kinematics, so you can get an idea for the dynamics of the system. So it's a really powerful tool. So before the days of this kind of integral field spectroscopy, when it came to looking at large spectroscopic samples of galaxies, we were really limited to aperture spectroscopy, in which we get a single spectrum from a galaxy, usually taken from its very center. So using huge samples of this kind of data, we made huge strides in our understanding of the relationship between galaxies and their emission lines. So for example, Cooley et al. In 2006 used this kind of data to develop new classification schemes, allowing us to easily classify galaxies into being star forming, into containing AGN, into all kinds of other things, just on the basis of their emission lines. However, this data is really limited in that we only obtain one data point for each galaxy, meaning that it's really difficult to disentangle the effects of global properties, such as stellar mass, from local properties, such as star formation rate, surface density. And the other thing is the light that we get is very biased towards the nucleus of the source. And so our source might be dominated by radiation from an AGN, and so we might classify it as an AGN, even though it has a lot of star formation going on. However, with integral field spectroscopy, by obtaining spectra along the face of a galaxy, we can actually use this technique to classify individual regions of a galaxy. So for example, this is a plot in the upcoming paper where I've taken all of the spaxels from all the galaxies in the SAMI survey and chucked them on this diagram. And so this kind of gives you an idea into the spatially resolved nature, into what's happening into our nearby galaxies. So the SAMI Galaxy Survey, as you'll learn about all tomorrow morning, gives us integral field spectroscopy for some 3,000 nearby galaxies. I'll leave the text specs to be explained by whoever's giving the talk tomorrow. But to cut a long story short, because we have this huge data set, we can take a really close look at the statistical properties of emission lines and connect them to the underlying mechanisms that transform galaxies over periods of their lives. Gas kinematics are particularly important, and SAMI is a great instrument to analyze gas kinematics because it's high spectral resolution. So this means that we can resolve the individual emission line components within each spaxel. So for example, in 2014, Eating Ho et al. Used SAMI observations of a starburst galaxy to identify the presence of a wind in the form of these multi-component emission lines in the asymmetric emission line profiles. And so now that the survey is complete, we can carry out this sort of analysis for over 3,000 galaxies, which gives us over 650,000 individual spaxels with emission lines. And so with this huge data set, we can do all kinds of cool stuff. So for example, we can split the overall sample into spaxels based on what their spectral classification is. So just as a disclaimer, these are based on the total fluxes in the emission lines, not the individual components. And so we can look at, say, the star-forming spaxels, and we see that less than 20% of these have 2 or 3 components. But if we look at spaxels dominated by radiation from a luminous AGN, that fraction goes up to 50% or more. And so to give you some ideas of the numbers here, around 92% of all these spaxels in SAMI with emission lines only have 1 component, only 7% have 2 components, and less than 1% have 3 components. So these are really quite rare. And so then with the sample, we can then ask questions such as what actually drives the number of components that we observe in each spaxel? So spaxels with more than one component tend to be associated with higher star formation rates and star formation rate surface densities. They also tend to be associated with younger stellar populations, which we can infer by looking at the D4000 angstrom break strength. They tend to be located at smaller radii, and they also tend to be found in more massive galaxies and galaxies with deeper gravitational potentials, which we can estimate by looking at the stellar mass divided by the effective radius. However, the most stark offset here is in the star formation rate surface density. So let's take a closer look at the star-forming spaxels. So here I'm showing exactly the same histograms, except I'm only showing those spaxels that have been classified as star-forming. And all of the same correlations remain. And in particular, we can see that the one component spaxels on average have star formation rate surface densities less than those of the multi-component spaxels by about 0.5 to 1 dex. So there is something significant going on there. So what do these individual components actually represent? Well, we know from the literature that the presence of multiple emission line components in star-forming galaxies has been used to detect winds driven by star formation. So for example, in 2021, Avery et al. Used unresolved spectroscopy from MANGA to classify galaxies as having outflows if they contained a broad second emission line component. These and other studies have also found that galaxies with or without these winds driven by star formation show very similar trends with mass, radius, star formation rate, etc., as we see when we compare the one component and the multi-component spaxels. So for example, these same authors found that galaxies hosting outflows tended to have much higher star formation rates and tended to be more massive than those galaxies that didn't contain outflows. So from this, we can infer that the presence of multiple components in these star-forming spaxels, at least, probably represents winds driven by star formation. And indeed, if we look at the fraction of spaxels containing 1, 2, or 3 components as a function of star formation rate surface density, there is a really clear increase, such that the spaxels with the highest star formation rate surface densities almost always have 2 or 3 components. And because we know that whether or not a star formation event will launch a wind is very, very dependent on the star formation rate surface density, we can then infer that the presence of multiple components is directly related to the presence of these winds. So how can we actually analyze these individual components? So unfortunately, due to signal to noise limitations, we only have H alpha fluxes for all the individual components. In each spaxel, we don't have the individual fluxes for things like H beta and O3, which you would need to do the classical spectral classification. So this means we can't do that. What do we have though? We have the gas kinematics. Importantly, we have the gas velocity dispersion, so the width of each emission line component. And it's known that these line widths correlate really strongly with the underlying excitation mechanism. So for example, in 2021, Laura et al. Found that spaxels in manga galaxies dominated by star formation tended to have very low velocity dispersions compared to those dominated by radiation from AGN or evolved stellar populations. We also have the H alpha equivalent width, which is essentially a measure of how strong the H alpha emission is compared to the stellar continuum. And this has been shown to be very effective at distinguishing emission from low energy sources such as ionized hot evolved stars from more energetic sources such as star formation and AGN and shocks and so forth. And so I've created a new diagram called the WHAV star diagram, title pending, which combines both of these quantities. So we have the H alpha equivalent width, and we also have this quantity called delta sigma, which is the difference between the gas and the stellar velocity dispersion. I've chosen this quantity because it's slightly less impacted by beam smearing than the velocity dispersion on its own. And also, Belfiore et al. In 2016 proposed that it might be an effective means of detecting kinematically disturbed gas with non-gravitational motions. So the actual diagram itself has the log of the H alpha equivalent width on the y-axis, and on the x-axis we have this delta sigma parameter. And in each of these panels here, I'm going to show distributions from all the spaxels in SAMI, the narrowest component. So if we look at the spectrum up here, that will correspond to the blue bit, and then the intermediate, which is the yellow, and then the broad component separately. So just looking at the narrow component, we can immediately see that almost all of these components cluster into quite a small region in this diagram. So the peak in this distribution is about -40 or so kilometers per second, and these mainly have intermediate to high equivalent widths. And keeping in mind that this is a log scale on the y-axis, sorry, on the color axis, there are actually very, very, very few components that lie in this kinematically disturbed region of the diagram. The distribution in the intermediate components looks very different. So the equivalent widths are shifted down, and also a large portion of these are in the right-hand side of this diagram. And we also see the formation of this long extended tail. And finally, the broadest component looks very similar to the second component, but skewed to even higher values of delta sigma. And so there's obviously a lot of interesting structure in this diagram. To give us an idea of what's actually driving this structure, we can color each of these cells by the median spectral classification of its parent spaxel. And so what we can see, focusing on the component 1 diagram, is that the upper left corner of this diagram is dominated by star-forming spaxels. And as we move down into lower equivalent widths, we pass through a region that is dominated by composite emission. So this is usually attributed to mixing between star formation and AGN, or star formation and ionization by evolved stars. And then finally, the very low equivalent width end, we have these liner spaxels, which due to their low equivalent widths, we can attribute to evolved stars. And so this feature is most likely just a mixing sequence. Meanwhile, if we look at the right-hand side, this is where we start to see some CFET spaxels, and there's also some ambiguous spaxels there. So this is what we would expect, because CFETs and ambiguous type spaxels, which are likely associated with AGN, post outflows, and that's where we expect to see kinematically disturbed gas. Meanwhile, if we look at the components 2 and component 3, there are a lot of star-forming spaxels in these diagrams, and we can see some more CFET activity happening as well. But let's focus on the star-forming spaxels for now. So here I'm showing the same diagram, but I'm only including the star-forming spaxels. And there are a few interesting things that we can take away. The first takeaway is that in nearly all star-forming spaxels, the first component is kinematically cold with delta sigma less than 0. And this applies even to the spaxels that have very, very, very high star formation rate surface densities. That's interesting. The other thing we can note is that the second and third components form this tail, which is skewed such that the equivalent width is anti-correlated with delta sigma. And if we look at particularly the component 3, there's this long tail that extends to very high values of delta sigma. And if we color each of these cells by the median star formation rate surface density, we can see very clearly that almost all of the spaxels containing these kinematically disturbed components have very high star formation rate surface densities, which is a bit of a smoking gun that these kinematically disturbed components that lie on the right-hand side of this diagram are linked with energetic star formation in winds. But there is a lot of spread in these diagrams. And so to give us an idea of what could drive this spread, we can create these diagrams in individual galaxies. So for example, here is a very photogenic face-on spiral galaxy in SAMI. In the central regions of this galaxy, there's quite a large region where there have been 2 or 3 components fitted to the emission lines. If you look at the BPT diagrams up here, the emission line ratios are consistent with star formation with maybe a little bit of shock mixing going on. And if we look at the WHAV diagram, which is shown at the bottom here, we can see that the second and third components, so there are these pink and orange diamonds, form this tail, which we saw in this diagram. And this immediately tells us that the spread in here is at least partially driven by local properties and not by global galaxy properties. And it turns out that this is actually a really common feature. So you can take basically any star-forming spiral galaxy in SAMI, and you'll see the formation of this kind of weird tail kind of structure in the WHAV star diagram. And so there's obviously some link going on here between star formation and winds and the presence of intermediate or broad components in each spaxel. And so what this tells us is this delta sigma parameter might be a good way to actually distinguish true winds in a spaxel from multiple components that could arise from observational effects such as beam smearing or simply line of sight geometry effects. And so we can define a kinematically disturbed component as having this delta sigma factor greater than 0 with 3 sigma significance. And if we plot the prevalence of these kinematically disturbed components as a function of the star formation rate surface density, we indeed see there's a really strong correlation there. But this is all very preliminary. And I think I'll just leave you with my summary there. Yes, I am actively looking for collaborators on this project. So if you're interested in learning more, come and find me. Also, before I finish up, Andrew and I are going bouldering tonight. So if you want to, if you would like to join us, come and find me after the session. Thanks.